All right. Well, then, good morning. Let's start our class today. Just so you know, next week is the midterm examination week, but we do not have midterm for our class. So we have no class anyway, right? You join the examination for the other subjects, and I see you after the midterm week. Okay, so it's gonna be 2 weeks from today. Anyway, today we're gonna talk about buffer overflow. And this slide actually, I took it from my, partly from my Ph.D. thesis several years ago. And it's one slide that I share with my professor. Okay. So let's see. Sure. Okay. Go. Does it work? From home, can you see my screen? Is everything okay? Okay, yes. Okay, anyway. Okay. So it's about buffer overflow, and if you ask me, I would say my PhD thesis is about buffer overflow. So this is actually my area of expertise. Anyway, let's focus on the part about buffer overflow. First of all, let me give you a little history about buffer overflow. And in case you don't know, the first well-known computer worm in the world, it came out in 1988. And we call it Molly's worm. That's partly because the person that created this worm, his name is Robert Mollis. So back then, Robert Mollis created this worm by using a security issue in a Unix machine running on the wax machine, and he actually do buffer overflow on a special program called Finger, which used to list the user who is online on the Unix machine back then. So by using the buffer overflow, he is able to inject his code into the server and use that server as a base to inject the code to another servers. At the end of the day, we have learned that global knowledge conquer about 10% of the internet. And this is 1988. That means if you want to use internet, maybe like for Shula, we have only one Unix machine that's around the campus. If you want to use that Unix machine, you may have to go to the main library and use terminal like that back then. And he got 10% of the internet. And since 1988, we continue to have several buffer overflow. And today, we still have buffer overflow. And just a little bit about Molly's worm, in case you find it to be interesting. Robert Morris created this firm when he was a college student like you. He was in, I cannot remember, second year or third year in college, in school, in university. He created this firm as an experiment, technically speaking. And when he learned that he might have caused something terrible, creating the first firm, right? We got the news said several things about Molly's firm. Like, oh, computer around the world are in trouble. Most unique machine is inaccessible. And one of my professor back then, he was at AT&T Bell Lab, and then he shared a story. He said he went to the lab in the morning, tried to log into his unique machine, unique terminal, and he found that his terminal is pretty slow. Like when he type A, it takes few minutes until A pop up, which is unusual then. And once he got in, he typed the PS, the process list command, and he found this figure D, like thousands of them. Then this is 1988, not that we have gigabytes of memory like nowadays. Back then we got maybe 4 megabytes, something like that, not that much. And when Robert Morris learned that, well, maybe he did something wrong, he did something very bad, he told his father, who back then was a professor in the university. He told his father that, well, Dad, that things that happens around the world that you see on the news, on the radio, maybe it's me. Maybe I did that. So his father called FBI and told FBI, say, well, the issue with computer around the world, you might, with the regarding the issue with computer around the world, maybe you want to talk to my son like that. So FBI took Robert Morris in, and people learn about Morris work, and that's the first time that we have big security issues in the computer world. So you may say Robert Morris is the first person that created virus or worm anyway. Well, that's 1988, and actually Robert Morris is still alive, and he's still working today. You want to guess where he is or what is he doing today? Want to guess? What? Jail? No. Robert Morris is now a professor at MIT. He is now a professor at MIT. So it's kind of funny story in a sense that he created a worm and became a professor. But nowadays, if you create a worm, you go to jail, right? And I cannot remember everything about the cases, the trial, but it ends up with something pretty funny, like Robert Morris was detained from using the computer or touching the keyboard for 6 months, like that. Again, that's 1988. If we talk about worms or buffer overflow nowadays, that's pretty severe. If you hack someone, if you distribute a worm, you get into trouble nowadays. And we keep having buffer overflow. Nowadays, 2024, 25, we still have buffer overflow. So I take a screenshot from CERT, the Security Emergency Response Team, which they basically collect the vulnerabilities around the world. And you may see several attacks, which actually it is buffer overflow behind the scene. So we still have buffer overflow. The quick question is why, or what is buffer overflow? Why for 30 years, we still have buffer overflow nowadays. And it still remains the fundamental of security issue today. Like this one, this is buffer overflow in 2003 from the slammer worm, which is the SQL slammer worm, the one that attacked Microsoft SQL server. Well, this is a little funny in a sense that the nuclear power plant decided to use Windows 2000 to run the nuclear power plant. Back then, I would not say it's a bad idea or good idea anyway, but they decide to use Windows 2000. And well, technically speaking, they have isolated network. You cannot plug in your USB drive or connect external network, no internet connection. So they should be fine, right? But well, it's United States, and if you take a look at United States, they have like 5 different time zones in the mainland. Like New York is evening, California is still afternoon, something like that. So they have 5 time zones, and sometimes they buy electricity across the zone. You may not know, but in the evening, it is the time that people use electricity the most. Because people go home, study heaters or air conditionings and so on. So the nuclear power plant, they allow contractor to dial in 56K modem and ask for electric switch to switch the power grid to a data zone like that. And that's the channel that the worm get in. Not a good idea anyway, but the worm get in from 56K modem from the phone line, say. So not a good idea, right? Anyway, we've been talking about this when we talk about trust in the past. So that incident, the electricity went out, the North America, the Northeast America was blackout for more than 6 hours. That's also caused by this worm. And several cases, the Bank of America ATM machine went down, so on. That's the worms. And we have continued to have buffer overflows and over and over and over again. So what is buffer overflow? What is buffer overflow? So I try to make you understand buffer overflow today in hope that if you understand buffer overflow, maybe you will be a better programmer, or you know how to prevent such a kind of attack. So let me start with this one. I got a single C program. Pretty straightforward. If you take a look at the code, it basically asks for your age and asks for your name. You type in your age, like maybe you type 15, 15 convert to integers, save here. You type in your name and then print. This person is years old, like that. So pretty straightforward. So let's try running this program. Okay, let's say I run this program like this. Okay, where's the problem? You see the problem, right? This one, I type 15. Somehow it changed to 49. So what happened? And why 49? while 15 changed to 49 in a sense. So if you take a look at the code, we have this. We got name and we got a buffer, okay, and we got a like when you type 15, you go here, and when you type your name, you see that I got 8 characters for name. How many characters did I type? 9. So this is what happened. You type 15, okay, and then you type 9 characters. So that 2 character overflow over the 8 variable. Why 49? The ASCII value of the character 1 is 49, right? Or in hex, that's 3 1, right? And since this is x86, and it use little endian, so we got 1. This is an example of buffer overflow. Pretty straightforward. But how bad can it be? In this case, it just made me older. And I'm not that old anyway. Just made me look older. Right? So from 15 to 49. And there are several cases like this where you type something, but wait, my other data changes. Okay. So in a sense, it's buffer overflow because you type this, it overflow to others. That's the name, buffer overflow. Let me give you another example, the extreme one. Okay, I think you have a computer architecture, right? Computer system architecture from Professor Prabhat, right? And back then, I used to taught that class to your senior, but I recently Professor Prabhat took over. So let's try this a little bit. It's about the call stack. Call stack. Yeah. So when you have a function call, and the parameters would pass on top of stack. So this would be I, this would be pointer P, like that. And this is the return address. For Intel anyway, Intel called return address instruction pointer. That's the name EIP, instruction pointer. And you got several variables. You got J, you got what, foo, you got FP, lots of variables. And eventually you got B, the buffer. Right? So bad guy would want to change the return address or maybe the function pointer, or maybe the frame pointer. If they can change that, maybe they can do something pretty bad to your machine. So let's see how bad can it be. Okay. All right. In this example, bad guy can send you a string, pointer p in this case, because it is a C program. String is basically a pointer to the character, right? So pointer p, bad guy have control over pointer p. And we do something stupid here because string copy didn't check for the length of the buffer. So we copy P to B. So what will happen if if P is longer than 128 buffer overflow course? So this is what the bad guy would do. The bad guy would try to insert malicious code into the buffer. Malicious code into the buffer. And then change this pointer back to this buffer. Right? With this, meaning that now I send you something, you would execute the code that I just sent to you. Meaning I can ask your computer to run any code that I want. Of course, you have to do this in binary. You have to do this in binary. So you create binary string has to program with buffer overflow vulnerabilities. If you success, your program would run my code. Sometimes people refer to this kind of attack remote execution. I send something to your computer. Now it runs my code. So technically speaking, I can ask your computer to do anything. And that's the bad guy. That's what the bad guy do. He inject your computer with malicious code. Ask your computer to do bad things like my Bitcoin for me or whatever. Right? So you may ask, this is actually how the worm get into your computer. I create the worm code, put it here. I somehow redirect your return address and point it to my worm code. Then boom, I got your computer. So I showed you two kinds of buffer overflow already. This one, change the variable. Make the data bad. Change the data. And this one, a little more severe, because now I can ask your computer to do whatever I want. Do whatever I want, or inject your computer with malicious code, like this. Okay. Another example. Another example. This one, I took it from another worm. I reverse engineer from another worm called Hawashi Sapper. Okay, pretty old worm, but I reverse engineer from it 20 years ago. Okay. Again, The idea is bad guy have control over something. Bad guy can send you an agreement and you do string copies. Okay? But this one, they do several steps of string copies and eventually redirect your computer to the malicious code. Okay, to understand this one, you have to understand one thing. We call it jump slot. Jump slot. Or sometimes some software call it delay slot. Anyway, let me explain. This is pretty common actually, but for those of you who may not familiar with system, operating system or architecture, you may find it, what is this? But let's try to understand it a little bit. In this example, we got printf. Printf. Well, in standard C library, we got the print function, the printf. Is it your code, the printf? Likely, no, because it's a part of the standard C library that comes with your operating system, come pre-installed with your computer, with your OS. So this is something that we call shared library. Or on Windows, we use another word for it. We call it dynamic link library, or you may refer to it as DLL. Windows call it DLL. But other systems like Mac or Linux, they call it shared library. Shared library. In a sense, shared library is the code that is not you. It's not your code. You share with others. So let me draw pictures of shared library a little bit. So it's like, this is your code, your program, and you got printf. When you compile this software, what happened is that your compiler will say, oh, you use code from others from the shared library. So the machine code will translate to something like called printf. And they would create a slot, say printf would be jump to something. Jump to something. And leave it like that. So when you compile the software, we see printf jump to something which we don't know. And when you try to start this software, to run this software, double click, whatever, you try to run this software. What your operating system would do is that they would load this code. Once this code is loaded, they will look at this section and see, oh, you want to use printf? We got printf in the memory shared by others. Like printf, for example. They would see that, oh, printf is like, for example, 8,000. So your operating system would put 8,000 into this slot. Right? So when you run your code, what happens is like this. Oh, you call printf, then we call it here, and then we jump here, and then we finish and return here. So that's how the shared library works in your computer. We got memories with shared library somewhere else. Everybody use the same copy. Fine. Right? You use printf, everybody use printf, call the same library, just like that. Your program would jump to that code. Once it return back to your code. Look pretty straightforward. Okay. So what the buffer overflow do is that they create a pointer to this slot and change this slot to point to the code that the bad guy want. Right? The malicious code here. Also buffer overflow attack. I change number here. So rather than call printf, you call my code. But the underlying issue still it is buffer overflow. Right. So the last call to buffer overflow here we call arbitrary code, the code that bad guy just put in. Or after code that the bad guy want you to call. Still, remote execution. You are not supposed to run that code. Somehow, I pass data to you. It changed your jump slot to call my code. Okay. For this one in particular, people already fix it. How they fix it? Well, straightforward solution. They make this area read-only after load the software. So nobody can change the jump slot once it is loaded. Yeah, so modern operating system fix this by say, oh no, you cannot change this. So modern kernel fix this. So there are several examples of buffer overflow attacks. I have several examples. I can go on until the end of the day, and you will find like that. All right. So I will start with the example of buffer overflows here. But we will learn more maybe after the midterm examination. We will learn a few more examples about buffer overflows in another class. But again, if you think about it a little bit. The underlying issue is that we have no protections. We have no boundary checking. Right? That's why we still have buffer overflow today. And you may have code like this anywhere in your program. And some of them, it took years until the bad guy learned, oh, we can use these vulnerabilities. There's a backing like that. So think about it a little bit. Why we have buffer overflow? To be able to do buffer overflow attack, maybe there are two conditions. First one is that bad guy can send something to you. I can send something to you. And that's something eventually you would redirect to use it. Right? Like I pass you a cup of tea, a cup of drink, I should say. I pass you a cup of drink. Somehow you manage to drink that, so you get into trouble. that like buffer overflow attack distance. Somebody pass a drink to you. Eventually, you drink it, so you get into trouble. In this case, bad guy pass data to you. Somehow you manage to misuse that data as a code. It's supposed to be data, not a program. You misuse it as a code, as a program. So you get into trouble. So scientifically, if you want to prevent buffer overflow, meaning you have to eliminate at least one condition. Do not accept the input or use it properly. Right? Do not accept input, or if you have to take input, use it properly, not as code. Use it as data. Like that. Okay. So that's the underlying concept of how we should prevent buffer overflow attacks. And well, this is partly taken from my publication in the past. So general idea is like this. People say, okay, we know what is buffer overflow. How could we prevent that? There are three main solutions, three main groups of solutions. First one, we call it statistical analysis. Static analysis, sorry, not statistical, static analysis, sorry. So static analysis, in a sense, it means you give me the source code. The tools would analyze the source code and try to give you a report on how to fix the code. So this one basically means fix the code. You give me the source code, I do the analysis and I say, hey, you should fix this line. You should do a bar checking here. All right, so that static analysis. Next one, we call it dynamic solution. Dynamic solution. In a sense, this is the runtime environment. The runtime environment that try to fix buffer overflow, try to detect or fix buffer overflow. Like if you run your code in my environment, I would sanitize some part of your code to fix it against buffer overflow attacks. And we got several kind of solutions down here, but we will take a look at it later. And another one, we call it isolation, or you may have heard of the word sandbox. We talked about this word before, sandbox. In a sense, I don't care whether your software, your piece of code got buffer overflow or not. I put it in a sandbox. If you have buffer overflow, it would be contained, would be in that sandbox like that. Okay, so this is a group of buffer overflow protection. So we will take a look at each categories. Static analysis. So what is static analysis? Well, technically speaking, static analysis, you send the source code to a tool. The tools would analyze your code and give a report. Like for example, we know that string copy is bad. So static analysis will say, hey, can you take the string copy out or replace it with something else better? Right? So who fixed the code? You. And sometimes they have false alarm, like there's no buffer overflow at all, but the tools just say, hey, don't use string copy. But there are several cases that string copy work just fine. We do not always have buffer overflow with string copy. So ideally, this is best. You fix the code, but it's not always that easy. Anyway, in case we switch. Okay. So there are lists of tools that I put on the line. Sometimes you may heard of the word link. Link. That's also static analysis. Link the code, find the problem. But they miss several things. When you link the code, so we would better try to do dynamic solution, the runtime solutions, dynamic solutions. And there are several proposals for the dynamic solutions. I group them together into 4 subgroups. I call it address protection, input protections, brown checkings, and obfuscation. So let's take a look at it one by one. Okay, let's try canary word. Let me jump to big pictures of canary. This one. Basically same pictures, but bigger, so it's easier to explain. Okay? It's like this. If you take a look at buffer overflow, you would see that you would overflow from buffer eventually to that code. So in a sense, buffer overflow only happens in one direction. It's like data coming in from the front door and get faster all the way. Okay, so this is buffer overflow happen in one direction. So a naive solution for buffer overflow would be like this. I want to protect return address. I don't want buffer overflow to override the return address. What I would do, I would put a known value between my buffer and the return address. Okay. So it would be like this when we have a call to my function. I would place a canary. Then I have my code, and then I check the canary before return, like this. So how does it work? Well, if the canary got modified, then I know that somebody already do buffer overflow on the code. If the canary is good, then maybe I'm okay. By the way, what is canary? But the bird, what kind of bird? Okay, good one. Yes. Mhm. So let me quickly do this. Canary. Canary bird. Mhm. Well, canary is a yellow bird. Or in Thai we call it what? Nok kamin, something like that. Yellow bird. Mhm. So it's like this. We have canary bird, and the coal miner would put canary in a small case and take down with him to the mine. This. So what is it? Why? Yes, yes, right. Uh-huh. Because, well, whether it's good or bad, that's up to you anyway. But the canary bird kind of sensitive to environment. If we have bad gas leak, toxic gas in the mine, the bird would die. If the bird just die, then we know that we are in trouble. Mhm. If the bird is good, okay, it's not that bad. We can still work here. So they still use it today. They still use it today. The underground miner, they would have small case of canary bird. The bird is healthy, okay. The bird is dying, okay, maybe we should run. We should evacuate. Mhm. That's the same idea when we use the word canary in buffer overflow protection. If the canary is good, we good. Canary is bad, then we are in trouble. Oops. Canary is bad, we are in trouble. All right. Question. If you happen to be a hacker, you know that your code is protected by a canary word. What would you do if you want to get in? Okay, I give you another example, maybe easier to understand. Let's say this classroom, okay. We got front door here. Right? I got something that I want to protect, so I put it in my asset here that I want to protect. I want to make sure that nobody get in. So I put a canary. My canary would be I paint the floor with a chalk, use the white chalk, paint the floor. That means if somebody get in, I would see footsteps on the floor. Right. Now you happen to be a bad guy, you want to get to my asset without me knowing that you have been in. What would you do? Hmm? Yeah, you would get in on your way out. You would draw the shop, get the shop on the floor again. So in this case, for the canary, so it's like, oh, I know that canary is number 5. So I would try to overflow and make sure that after the overflow, this location is still number 5. If that is the case, then I can still get in. And I can, technically speaking, bypass the canary protection. Bypass the canary protection. Mhm. And that's how it works. People propose that we do canary word protection. And a few weeks later, the hacker came out and said, hey, what have you done? It's nothing. And modern compilers, they still do this. They may have different name for it, but same technique. Microsoft also do this with Microsoft compiler. Okay. Yes. So we see that canary you can bypass. Again, in details, who created a canary is also an issue. The operating system created for you or the compiler. If it is the compiler, you can just disassemble the code and see everything. So it's just not working in a sense, right? So this one is not working. And let me try this. Address encode. Where is that? Address encode. Okay, this one. Okay. This proposal suggests that, oh, bad guy want to overflow your data here. So rather than just put raw data on top of the memory, I would encode it or encrypt it. By encrypting the data, if that guy do buffer overflow, it would be random, right? It's like before I put my data on this table, I would encrypt it. Now you try to overflow the table, flood the table with something else. When I took my data back, I decrypt it, it would be random. So it's not that you cannot do buffer overflow, but when you do buffer overflow, it would not be effective. The result would be random. Okay. You think this is a good idea? Well, people do not do this. Why? Because it's expensive. Why I say it's expensive? Because you use the return address or you use call return all the time. We always do call and return all the time. We always have function pointer. And the call and return already expensive. It took several cycles, maybe 2 or 3 cycles comparing to normal operations. Right? If you don't know what I'm talking about, go back and revisit your architecture class. They talk about this. Right? So let's say if call and return took you 4 cycles. If I say do encryption and it take cycles to do call and return, it would be real expensive, right? Or if you decide to do single encryption, that means no protection at all. Right? That's not a good idea. No protection at all. Oh, and we already talked about exclusive all right. That's a simple kind of encryption. Mhm. So technically speaking, this is not a good idea. So you should not do this. So we will say no. It's expensive. We should not do this. How about this? Okay, copy of address. Let's see. Okay, this one. Okay, let's try this one. So normally your computer would put local variable, return address, and function pointers. Technically speaking, the target of the bad guy, the things that bad guy want to change in your software, they would put on the stack memory. So when we do buffer overflow, it would be that we overflow something here, right? So people would propose that a simple solution would be, hey, this is sensitive, this is sensitive, this is sensitive, so we put it here. They have special stack, they call it control stack, like the return address. We put it here, so nobody can touch it. It's like this. I said, hey, I got a piece of paper and this is important. So when I put it down, I make a copy and put it somewhere else. Right? When I have to use it, pick it up, verify with another copy. Oh, it's the same. I'm good. Right? So this is another proposal for buffer overflow. Is it a good idea? Not really. Not really. And some people even propose architectural solutions for that. But I saw a case that, oh, we do buffer overflow here and here. You may have to do it several times, but eventually you've got a copy here and there, so I do buffer overflow here and then over there one more time. Much more difficult, but still possible in several cases. Mhm. And there are several proposals. One say, okay, we use spatial area in the memory. One say we use cache to save another copy. And technically speaking, I call them shadow storage. You got real copy, so you make a shadow, put it somewhere else. Okay. Again, this is also not universal. And this one we call tag architectures, which is pretty specific to IBM mainframe. IBM got a special memory that they call tag memory. The idea is that for a special address, special data, they would have a tag. And if you want to read or write to that data, you need special instruction. So technically speaking, you just protect that memory with the tag. But this would only work with special architectures. Only special architectures. And let's try to understand this by checking. Where is it? Okay, this one. Bound checking. So it's like this. When you write your code in C, like when you create a character A, in the past, we would have, oh, A point here. A is a pointer to this area of memory. And there's no boundary. So bound checking, basically, we propose that our pointer is now a special kind of pointer, enhanced pointer. We got a base start here, and we know that the limit is here. You cannot go beyond this limit. So special version of pointer. When you do the access, you do check whether it's in the boundary or not. So in a sense, this is totally eliminate buffer overflow. Why? Because now you cannot write beyond the boundary. So this is a good solution in a sense. And in fact, when you use something like Java, Python, or several programming languages nowadays, they would do this for you behind the scene. Right, in Java, you do not have to specify what is the size of your string. You just say, I want a string. Right? In Python, you just say, I got a string, done. It can be 100 characters, 2 characters, 400 characters. It's a string, done. So modern programming languages, they do bound checking for you. And technically speaking, we should not have buffer overflow with those languages. Right? But, well, in reality, we also have this. In reality, we also have buffer overflow in Java, in Perl, in Python, in several languages that claim to be type safe. My question is why? You know why? Believe it or not, we still have buffer overflow in Java. We still have buffer overflow in Kotlin or in Python or whatever, .NET. You happen to know why? Well, technically speaking, you should be okay, right? Because the language, the runtime environment do the bound checking for you. But it's like this. Java, you will run Java using the Java virtual machine, JVM, JRE, whatever you want to call it. The JVM, the JRE created in C programming language, in C++. And most of the time when you do Java optimization, you would do a native call to C or C++ library. That's where the buffer overflow happens when you cross the boundary between languages. Same thing. You said you write Python. No, the Python runtime is C. You do print in Python, it's eventually called printf in C. Several library that you use in Python is actually called to native C library. So I would say we still have underlying mechanisms that is vulnerable to buffer overflow. Okay. Or we even have people suggest that we have no okay, people also suggest that we have no protection mechanism that is perfect for buffer overflow. So maybe we should implement every single piece of code. That way we can avoid buffer overflow. The person that said this is actually Microsoft. And people would ask, do you believe it? Do you really believe it? And Microsoft say no. So we still have buffer overflow. Okay. So what else do we have? Okay, we got the canary word, the address protection, the copy of address tag, and we have bound checking, which is good, which is good. But again, this is slow. Why this is slow? Because now you do check whenever you access the memory. Like I want to read something, you would have, oh, is it in the boundary or not? Okay, it's in the boundary, I can read. Now I want to write something, is it in the boundary or not? Okay, it's in the boundary, I can write. I want to write something, is it in the boundary or not? No, it's beyond the boundary. Okay, we create a new string for you, copy it, and you can go to the end. So it's slow. And that's also explain why Java or Python, technically speaking, would be slower than C or C++. Because we do bound checking, the runtime environment do the dynamic bound checking for you. For security, that's better. But for performance, no. And in fact, there was an experiment showing that we got the same piece of code, one with bound checking, one without bound checking, and it like 3 times slower. And people they got a word in English. They say that race between performance and security, performance always wins, something like that. So it's just ask yourself if you have to buy a computer or a piece of software. You would say you want high performance or you want the secure software. Most of the time, people would say they want high performance, right? In the past, anyway. So when we say bound checking, it's good, but you trade off with performance. Whether it's a good idea or not, that's up to you. But more than programming language, they do the bound checking. Well, in the past, a friend of mine actually tried to argue with me that Java would be faster comparing to C++. I say no, impossible. Because if you understand bound checking, you would say there is no way that Java would outperform C or C++. But nowadays, if you write your software in Java, sometimes it's faster than C or C++. Why? Wanna guess? You're technically speaking, Java would be slower, right? Because Java always perform bound checking. Well, because nowadays, when you write your program in Java, sometimes the Java virtual machine would do multi-threading for you. If you write your program in C or C++, if you want to do multi-threading, you have to do it yourself. But with Java, you write standard Java, the runtime would do 3 or 4 threads for you. May sound funny, but I would say if you are stupid, write Java, because the Java runtime environment may outsmart you. But if you are smart enough, write C++, you can get the best of everything. But you have to be smart enough to outsmart the Java runtime. Okay, don't have to take my word for that. It's a joke in a sense. Okay. But if you ask me, I would say it's a problem in the language itself. Because when you write Java, you don't have to think about several things. You just ignore and you leave it to the Java runtime. But when you have to switch from Java back to C or C++, then you ignore several things and you get into trouble. So previously, when we do C or C++, programmer is pretty good person. I mean, they're pretty good at the details, critical thinkings. But nowadays, modern programmer, they just do Python and Java and they ignore several things. And I say that's bad from the system point of view. Because you never care about how many gigabyte of memory you use. You just say, I want memory. But with C and C++, you have to think, oh, I need this, I need that. I have to return the memory here and there. Okay. Anyway, I'm not blaming anyone, just the trend anyway. If you ask me if I have to write something, I do not always go to C++. That's also a stupid idea. All right. So, several cases I would use Java or Python. But for certain things, I would say, oh no, you should use C++. Okay. Okay. All right. So this seems to be a solution that people go to today with the trade-off of performance. But again, bound checking is pretty high level. We do not have solution at the lower level. So if you do a native call to C or C++ library, then solve it. Right? And next one, we call it, well, this is one difficult word to pronounce anyway. If my memory serves the correct pronunciation, it's like obfuscation. Obfuscation, like the word confuse. So it's like this. Obfuscation means you make it difficult to understand your code. But it doesn't make the attack impossible. Let me give you an example, okay? Let me go back to my slide here. This one, buffer overflow. Well, if it's 20 years ago, you give me this piece of code and you ask me whether I can do buffer overflow or not, I would say easy. Why I say easy? Because I know that, oh, temp, 20 characters, name, 8 characters, age, 4 bytes, and we would have base pointer and return addresses here. So you ask me to overflow from here to here, I would just count 20, 28, 24 is 32 bytes from here. That's easy. I can just do it by hand 20 years ago. But nowadays, the compiler would say, oh, we maybe put something random here, put some random string here. So I can no longer count from here to here. It would no longer be 32 characters. That's not straightforward. And that's what we call obfuscation. Do some random number. Insert something here. Move the code there and do shuffle the memory layout. But still, it's possible, right? Even though it's 80 characters, I can still do buffer overflow with 80 characters. It's still possible. So that doesn't make it impossible, just make it difficult. So let's see. We call it security by obscurity. Which one? Go. So you land on something. Do some random, which make it difficult for hacker to guess the size of the buffer. So I would say it's not a good solution, but better than nothing. And in the past, Microsoft came out, I cannot remember, maybe in 2013, if my memory serves. Microsoft got a press conference and said, with Windows 2013 servers, Microsoft will implement this kind of securities. And Microsoft claimed that buffer overflow would now be difficult or impossible. And when Microsoft released Windows 2013 servers, like 2 or 3 weeks later, a hacker came out and said, I got you, Microsoft. You said this is a solution, and I also got another way to bypass it. So this is not perfect. So, but it means, how to say, no voice attackers run away. And your Mac OS nowadays, they put it maybe another step further. Every time you run, they will do some random memory allocation. So again, not impossible, just difficult. Okay, and a little bit about the tech architectures, the input protection. Its general idea is like this. We got a boundary between untrustworthy domain or user, and this is your code. Whenever we pass data, the idea is that we should mark it as untrusted. So we can use tag memory to mean untrust. So it's like this, like you give me a cup of water. You give me a cup of water. With input protection, I would put dye red color into that water to make sure that I will not accidentally drink it. Right? You give me water, I say, oh, I should not drink this. So I dye red color, green color into that water, so I will not drink it. So whenever I pick up my cup of water and I see the dye color, I would say, oh no, I'm in trouble. I should not drink it. So there are several solutions that use this idea. And actually, one of my research in the past also based on this idea. Input is bad, so I should not use input. Okay. And there is one solution that they call NX, which is basically a sandbox. This one is actually used in some version of Windows today and available on AMD and Intel processor. Not a good idea, but this is how it works. It's like this. So they say we got memory, and most of the time we would partition our memory into code and data, like this. So this solution say this part should not be executed. You can only run code in this area, but not this area. So make some part of memory unavailable for execution. And that's called NX. Make it read only. Make it that you cannot use it as a code. Which in turn breaks several programs. When Microsoft released the NX hash to Windows kernel several years ago, it breaks several programs. One of it is Photoshop. Photoshop also break like the virtualization. Like VMware, like that, break several things. Why? Because there are several kind of optimization. Maybe not really about this topic, but maybe you have heard of it. Trampoline. You know the trampoline? The jumping springboard, something, yeah, trampoline. There are a kind of optimization that we call trampoline. And some mechanism like this would break the trampoline. Let me quickly explain the trampoline a little bit. So, for example, you use, okay, let me give you a specific example. Let's say you use Photoshop. One thing nice about the Photoshop software is that when you run Photoshop would think whether what kind of processor that you are using. What kind of processor, what kind of machine that you are using. And Photoshop would dynamically create code that's suitable for your processor on top of stack memory, and then jump to run that code. For example, Photoshop may learn that, oh, your computer got a GPU. So let's use it. So they dynamically create a code that use GPU. Oh, you use the version of Intel processor with AVX with the vectorization unit. So we create a better code for the vectorization unit. So when you run Photoshop, it's kind of optimized for your CPU dynamically. And they create dynamic code in user space. So the NX say the user space cannot be executed, that breaks Photoshop. And you have to turn it off. So anyway, it's not perfect. The solution is not perfect, but and several people avoid it because it breaks several software. Let's skip some of them. And this one, well, this one is another kind of sandbox actually, and it is a part of the TPM module. Maybe you heard of the TPM. You know the TPM? The Trusted Platform Module, a special chip in your computer. Okay. Nowadays, modern computer, they would have special chip they call TPM, basically encryption chip bundled with your computer. A TPM module. And the TPM is like this. They would run your software in spatial memory, which is encrypted. Well, this is nothing about buffer overflow, but in the past, several people say this is a solution against buffer overflow attacks. And I say no, it's just trusted environment for spatial code that would prevent you from disassemble the code, something like that. So trust doesn't mean secure. But most of the time, people confuse about trust and secure, and I say that is bad. Okay. All right. So far, I told you several things about buffer overflow and how people try to fix it, try to create a runtime environment to prevent it, try to find a workaround for it. But still, we have buffer overflow today. Why? Simple, right? Because some solution we can easily bypass it. Like the canary, you put a canary. I said, I know the canary, so I just overflow and make sure the canary stay the same. Some solution just make it difficult to do buffer overflow, but not impossible. So just raising the bar, but not make it impossible. Some solutions seem to be good, but you have to trade off with performance, and people sometimes turn it off in favor of performance. Some got compatibility issues. If you use it, you cannot use your old code. Some library may not work. Some program may fail. So people avoid that. And some solution, you might need a new processor. Right? So put it all together. That's maybe why we still have buffer overflow. And in fact, I am not the only person who works with buffer overflow problems. There are several people talk about buffer overflows. And this one was said in 1972, and people say by the year 2000 we should have what byword protection. Technically speaking, no buffer overflow. But now we are in 2024, 25, we still have buffer overflow because the world is not perfect. Talk about this. And just a little bit about my solutions, my research, so you know what have I done and like this. Let me skip to this. Okay, let me explain with these pictures. Okay, let me explain with this one. Well, this is my PhD thesis several years ago, just so you got the idea. It's also solution for buffer overflow. But the idea is like this. We have buffer overflow, right? So my idea is, if somebody casts data to your software, I would mark that data as input, put the number 1 on it. Whenever I pick up a piece of data that I want to use, if it is handed, it is marked, it's bad. So I cannot use it. So technically speaking, I stop buffer overflow without changing a single line of your code. I just change the underlying architectures. Modify the CPU a little bit, modify the kernel a little bit to mark your data. Mhm. Okay, so it is actually a combination of tag architectures and input protection. That's my research anyway. Uh, And got a proof, which is not that important. We got details about implementation, and that's not important to the class. Let's skip this. Okay. Okay. So technically speaking, if you run the same software, one on my spatial architecture on the right-hand side, the buffer overflow would be stopped right away without modify a single line of code. I got emulator that would simulate this, and in fact I got patent on this, and I talked to Intel and Motorola and several processor company about my patent in the past. But eventually they decided they will not implement this into the processor because they was afraid that it would not be, how to say, it would consume too many power. Yeah, that's the argument. It would consume more battery because we add another bit to the memory and consume more memory. And the processor guy, the Motorola guy, say no. If it consume more memory, we will not do it. So that's how I got. Yeah. If they say yes, maybe right now I would be at Intel, but they say no, so I'm here. Just joking, but I have to be back anyway. I'm a scholarship student, so I have to come back. Mhm. Okay, that's for the lecture today. Uh, Maybe we have about 15-minute breaks and come back and take a look at the activities. It's pretty difficult, maybe for you. Okay, let's have 15-minute breaks.
อาจารย์ครับอาจารย์ลืมเปิดไมค์ป่ะครับ
อ๋อโอเคครับจะลืมครับโอเคครับอ่ะ okay so first thing just make sure that you can compile hello world and you can make GCC working you can do the object dump like this let me quickly I jump to my Linux machine and show it to you okay let's try the hello world a little bit So if you can compile the software, you can do the object dump. The minus d in disassembly. Yeah. I got a binary hello and I do the object dump. This is the assembly code of my hello world. This is the main function, and you see a call to printf like this. Okay, this is hello world basically. So if you got to this point, that means you are ready to do the activities like that. And you might want to try no stack protectors and no PIE on Linux to disable the obfuscation just to make your life easier. Again, I will propose here for the activity so that you understand buffer overflow, which is the fundamentals, the underlying issues of several viruses and worms. So I do not ask you to create a virus or worm, but I want you to understand how virus and worm works, right? And that would bring us to exercise number 1. For the exercise number 1, basically I print the main function, I print my function, and I try to print the return address like this. And I got my function that would basically print out the memory. Just loop and print the memory, right? So if you run it, you would see something like this. See, I print the main function, the my function, and the return address. And your result would be completely different from mine. Why? Because we got different operating system, different versions of compilers, different versions of several things. So it could produce different kind of binary, different address. It won't be the same. It would completely different. And what I want you to do from exercise number 1 is that I want you to understand stack layout, the memory layout of your software. So think about it a little bit when you make a function call. Yeah. What we will see is that we will see an I on top of the stack, and you would see the buffer. Between I and buffer, you will see the return address. So if I print it out, likely you will see the return address. And to make your life easier, I even put a label here and print the return address for you. So in this example, this is the return address. This is the return address, right? So from the stack, you should see the return address. Right? Where is the return address? And to make your life easier, I put in string here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8. So you would see here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8 here. See? And the return address would end with 41AB. So if you look at the memory, you would see here 41AB. This is the return address. Right? C941AB. The return address. So you will learn about the memory layout of your software. When you write the C code, you find the return address, which is up here. But in the machine level. Okay. What you have to do, you have to tell me which one is the buff, which one is the stack memory. Sorry, which one is the return address, so on. Okay. So draw a stack and maybe circle. Oh, this is the return address. Oh, this is the buffer. This is the variable I. So you will learn the stack. So I'm okay if you print a solution like this and you just circle for me. Oh, this is the buff. This is the return address. I'm okay with that. Again, the purpose is that you learn the layout of your memory. That's for the first one. Okay. And when you run the real software, this is going to show something like this. Again, your number would be different from my number. And you can see this. Right? Now, exercise number two. This is stack smashing. Stack smashing. What is stack smashing? Again, I put similar layout in my code. You would see main function, my function, and we have a function called greeting, which is up here. Greeting. So greeting would basically print welcome to exercise number 2, like that. If you see the code, you would see that, oh, I have a call to greeting, and then I call a concat agreement functions here. Your assignment is overflow the concat agreement function. Overflow the return address from the argument function so that once it returns, rather than returning to the main function, return it to greeting. So if you run the software, normally it will show something like this. Done. But if you do it right, you will pass something to it and it would overflow the return address and call greeting again. So I overflow, change the program flow to return to greeting. So you would see a second greeting. Right? Normal program should call greeting only once. Now you overflow the return address, it returns to greeting. So you see greeting for the second time. And once it returns from greeting, it's done. Segmentation fault. And this exercise would hint you along the way how to get the address of greeting. Like you may, in reality, you would not we would not print the greeting out for you. That's too easy. But just for exercise, I give you the hint. Normally, you would do like this. You would object down and you try to understand the code of the target. This one, EX2. Mm-hmm. You see, oh, there's several things here, but wait, I can find greeting. This is the address of greeting. So what I should do, I should create a buffer that would pass this address, replace the return address with this address, and it would return to greeting. And I give you a Python code that would give you a little help on this. It doesn't have to be Python. You can do it in any programming languages, but in this case, I can use Python. So in fact, I already do that for you. So we have, oh, this one is in C actually. So in this case, we got the wrapper code in C that try to inject this. But in reality, the tricky part is you have to figure out how many bytes does it take from concat argument function here to get to the return address, right? So if it is old compiler, you can just count that, oh, I got buff, and I want to go from buff to the return address. So it would be 20 plus the return at the base pointer. So it would be 24 bytes to get to the return address. But in this case, no, because we got some kind of obfuscation and the memory alignment. So what you have to do is that you might want to go back to exercise number 1 and do the counting. And you would see that oh, from this buffer to get to the return address, how many bytes? Again, your machine would differ from my machine. In this case, if you count, you would get number 40 in my example here. So I create a buffer, and at the byte number 40, I put the address of greeting. Right? So that way, when I do, sorry. I would get greeting the second time. Right? So basically, I ask you to do buffer overflow with this example code. Again, this is easy because now you see the source code. Real hacker would not see the source code. They would only see the binary, and you have to disassemble to understand the code. So, all right, this is one example of what the bad guy can do to your piece of code. Stack smashing, one type of buffer overflow attack, the easiest type of buffer overflow attack. Okay. And little hint down here, if you use some version of compiler, you might want to disable the canary, the stack protection. Depends on what version of compiler you're using anyway. All right. So that's the easy part. And last one. Here. I got a piece of code for you. This is pre-built for Linux anyway. So you can download it from here if you want. Go and get it. Or you can build one yourself. To make it easier, you can build one yourself. So it's like this. If you take a look at the code, you will see that we have no call to the shell function. There is no call to the shell function at all. Right? No call to the shell function. But if you somehow can overflow the vulnerable function, replace the return address of the vulnerable function, maybe you can call the shell function here. So a challenge is that, can you call the shell function? Can you make a buffer, cache it to this software, to this code, and make it call the shell function? And I ask you to use netcat, which we used in the class last time. Make it a little server. And you use the telnet lib here to connect it and pass the buffer. So if you got it right, you got it to work, you got it right, you would get a shell in return. Yeah, if you run the code, it would be like this. And if you got it right, it would show you something like this. Okay, anyway, this is just quick demonstration. I don't have my Linux machine with me today, so I remote to server in my office. But you would take some time to master this. All right. And lastly, from number 4, this is a bonus actually. For exercise number 2 and number 3, if you use the no stack protector flag up here, sorry, no stack protection flag up here, that's easy. But if you bring it out, meaning turn it off, they would put some canary in your code, which make it difficult to do buffer overflow attacks. So number 4 is, can you do it even with the canary protection? No, the answer is yes. So this is a bonus if you want to do it. The real hacker can do it. All right. Again, not that I want you to be a hacker, but I want you to learn this is how hackers attack your software. Right? Real hacker would not see the C code. They only disassemble the software and try to understand the assembly code. So this is easy. This is a simplified version so that you understand what will the hacker do. Right? And number 5, just have to answer the question. So there are 3 questions actually. The first one is, most viruses and worms use buffer overflow as a basis for the attack. Do you think that exploit buffer overflow attack is trivial or is easy to do? Well, based on your exercise, it's easy. Easy or not, but the hacker do it anyway. Right? Hackers say something like, if there is a way, we will get in. That's what the hacker say. If there is a way, they will get in. Okay. And another question is, what if, as a programmer, how would you prevent your software from this kind of attack? So it's two sides of a coin. One question is, do you think it's easy as a hacker to get in? Another question is, as a programmer, can you prevent this kind of attack? And I put in this picture of Master Yoda from Star Wars that would cheer you up, but that would cheer you up or not, that I don't know. But it's not easy in a sense. You have to practice. Okay. So this is halfway in between. I didn't ask you to hack anyone, but I challenge you to learn how the hacker works. And I can do it easily, of course, because I got Ph.D. in this kind of buffer overflow attacks. So you ask me, this is easy for me because real attackers would not do something this easy. So this again, this is simplified version. Want you to learn buffer overflow. Okay, and I used to run this activity for a master students, and the master student, a group of master students say, "Oh no, I don't want to be a Jedi." It's just funny things anyway. All right, I think I will call it a day for now and let you do it on your own because it's gonna take some time, and sometime I walk around the class and see how you do, and I don't think this is the case for today because it would take just few hours to do. It wouldn't make sense to keep you here that long. Okay, do we have any question about these activities? And you should see this screen once you've got it work. Okay, so let's call it a day. Maybe use participation, right? No. Okay, before we do, let's do this. Click switch, right? Evelyn,
ตูมค่ะ
Narin, Shaba, ชวันวิทย์ครับผมณทัศน์เริ่มอ่านไม่ค่อยเห็นครับส่วนนัดดนัย
ครับผม
Oops. นัฐกิจครับดลพัตราไทยนะนนทพัฒน์
พร้อมเพรียงครับ
นะครับบรรทวัน
I'm here ค่ะ
ครับปรีประชา
ซูมครับอาจารย์
ครับปัณวิทย์
อินเดอร์ซูมครับ
ปุระวิทย์ ทัศนรี
Come here ค่ะ
ภาวัตพิษพิษชา
ขึ้นซูมครับ
หมายถึงคุณพิษใช่ไหมตะกี้
ใช่ครับ
ค
พิ
รับ
ซซ่าอินโซมค่ะ
ครับพานุพัฒน์
ซูมครับ
พานุรุต
ซูมครับ
ภูวิน
ซูมครับ
วิศธน
ซูมครับ
วิชยา
ซูมครับ
ครับศิลภพสืบตระกูล
ซูมครับ
สุขิริน
ซูมครับ
อนันตยา
ซูมค่ะ
Okay. Missing someone here? I think that's it for today. Then thank you. Enjoy your activity.